Imagine for a moment a digital fire hose. It's constantly skewing information, right? Data flowing, always moving. But what happens when that fire hose doesn't just spew, but turns into a full-blown tsunami? How do organizations out there, the ones running our digital world, possibly handle these unpredictable data surges without everything grinding to a screeching halt? That's our big question for this deep dive. We're going to pull back the curtain on volume-aware streaming systems and intelligent buffering. Think of it as your shortcut to understanding how digital infrastructures stay rock solid and performant, even when data feels like absolute chaos.
It's a fantastic question because, naive continuous ingestion simply won't cut it in modern streaming architectures. Data volume can explode in seconds, and if you're not ready, you're looking at system instability, performance bottlenecks, potentially lost data even. That's why intelligent buffering and truly volume-aware data handling aren't just good ideas. They're, well, critical design strategies. They ensure system resilience and efficient processing, enhancing scalability, reducing latency risks, and preserving stability during those, unpredictable data bursts. For any enterprise, this is absolutely essential for sustaining high-performance, real-time analytics in today's dynamic environments.
Okay, I'm really curious about this volume-aware concept. It sounds like the holy grail for data systems, but what does it actually entail? Where do we begin to become truly aware of our data's volume? Our source lays out a fascinating step-by-step strategy.
That's a great way to put it, because what we're about to walk through is essentially a comprehensive blueprint for designing resilient, real-time data pipelines. And it all starts with really knowing your data. So, step one, ingestion layer data volume profiling. What we're aiming for here is pretty straightforward, truly grasping those incoming data rates, spike patterns, batch sizes, and even individual record sizes. Because, honestly, you can't manage what you don't measure.
Right.
You'll often see techniques like using a schema registry, say console and schema registry, which helps enforce data consistency across different systems.
Ah, so it validates formats.
Exactly, validates formats. Then you layer on metrics tools like Kafka metrics, CloudWatch, or Datadog to track those sudden spikes. You'd also profile by time bucket thinking in terms of like 5 seconds, 30 seconds, 1 minute, using aggregations in tools like Spark or Flink.
So, if I'm understanding this correctly, the core idea is that accurate measurement at the ingestion layer isn't just about data, it's about predicting and preventing future bottlenecks.
Precisely. The real takeaway here is that profiling isn't just data collection. It's sort of preventative medicine for your entire streaming pipeline. And that leads directly to the next critical step, buffering before computation.
Okay.
Because once you understand your data patterns, you need a way to absorb those shocks before they hit your core compute.
Like a shock absorber.
Exactly. Think of it as a shock absorber for your system, protecting your precious processors. This commonly involves leveraging messaging queues, like Kafka, Pulsar,
Assist too?
Kinesis. They act as buffering layers, retaining messages for retry or, backpressure. You might also see auto-scaling partitions based on transactions per second, maybe using Kafka with a tool like Cruise Control, which dynamically helps balance Kafka cluster loads, or even specialized tools like Fluent or NiFi, which often act as disk-based queues right at the edge, capturing data before it even hits your main network.
So Uber, for example, uses Kafka to buffer their GPS and trip events before processing them via Flink, dynamically scaling partitions based on rider volume. That makes total sense. You don't want a sudden surge of ride requests crashing your whole system. Once it's buffered, what's the next challenge we tackle?
Precisely. Once data is safely buffered, the next challenge is ensuring we don't overwhelm the core stream processor itself. That brings us to step 3, the pre-processing layer for controlled ingestion.
Okay, controlled ingestion.
This is where we get strategic. You might trigger microbatches based on volume thresholds, perhaps, 1 MAB or 10,000 records or fixed time windows, like every 10 seconds. You're also looking at performing deduplication and compression here before the data even hits core processing.
For the heavy lifting.
Right. Often using tools like Delta Live Tables or Kafka Streams, and dynamic batching using watermarks with Apache Flink or Spark structured streaming is key here too.
This sounds like a crucial step for efficiency. I know Amazon, for instance, uses microbatches with Spark structured streaming to handle high-frequency clickstream data. That must save them a fortune while still preserving their service-level agreements, their SLAs. But even with pre-processing, what happens if the downstream system just, can't keep up?
That's where step 4, backpressure and flow control, comes in. Think of it like a traffic cop for your data.
Or maybe a bouncer.
Oh, yeah, or a bouncer at a very popular club. You can only let so many people in before the place explodes. This prevents downstream failure from upstream overload. Techniques here include built-in backpressure in Spark or Flink, which automatically slows input if downstream sinks can't keep up. Other methods involve rate limiting right at the source ingestion and using windowed aggregation to kind of smooth out those volume bursts.
Right, like LinkedIn. They use Apache Samazo with built-in backpressure to manage profile activity streams during traffic surges. It's almost like the system is communicating its capacity limitations in real time. What happens if, despite all these controls, there's still an unexpected massive surge? Do we just drop data?
Good question. That leads us to step 5. Intermediate storage volume protection. This is your ultimate safety net. The aim here is to temporarily store that bursty data for decoupled processing. Instead of dropping it, you write it to data lakes like Delta Lake or S3.
In those microbatches again.
In the same microbatches, yeah, for later enrichment or replay. Another common strategy is using Change Data Cacher, or CDC, to persist incremental changes from databases.
So Cerner, the healthcare company, uses Azure Event Hub feeding into Delta Lake with volume-based buffer rights to support patient telemetry streaming. That's a powerful example. Using intermediate storage to ensure no critical patient data is lost, even during spikes.
Oh.
With all this sophisticated handling, how do systems avoid overspending on resources during lulls and then, scrambling during peaks?
That brings us perfectly to step 6. Volume adaptive scheduling and autoscaling. This is all about dynamically adjusting your compute resources based on the current load, so you're optimizing both costs and performance.
Makes sense.
We're talking about using autoscaling clusters, like those found in Databricks, or Flink Task Manager autoscaling on Kubernetes. You can even leverage serverless execution with platforms like AWS Lambda or Azure Functions for, say, low-volume events that can scale all the way down to 0.
Spotify does this, right? Using GCP Dataflow to stream user events and autoscale processing jobs based on region-specific load. That's incredibly smart. So we've designed, buffered, controlled, stored, and scaled. What's the final piece of the puzzle to ensure everything's, actually running smoothly?
The 7th and absolutely critical step is observability and governance. The goal here is to continuously monitor your system, understand its health, and receive alerts when volume deviates significantly from the baseline.
Got it. The warning system.
Exactly. This involves using monitoring tools, think Prometheus, Grafana, Datadog, or OpenTelemetry, to observe ingestion volume, throughput, latency, all the key metrics. You then set up alert thresholds and, crucially, implement auto-remediation, such as maybe auto-pausing stream ingestion or reallocating partitions if things get hairy.
I know Slack monitors their Kafka ingestion layers to auto-alert operations teams on ingestion delays or overflows during system outages. It's like having a digital nervous system for your data pipeline. So what does this all mean for someone actually building these systems? How do these sophisticated strategies translate into real-world code and configurations?
Well, at a conceptual level, it really boils down to a few key takeaways. Buffering is crucial for avoiding compute pressure from spikes. That's number 1. Backpressure is essential for preventing upstream systems from overwhelming slower downstream ones. You need that control. Dynamic batching improves cost efficiency and reduces latency. Smart processing. And finally, volume-aware scaling prevents failures and optimizes compute usage. These are really the pillars.
Okay, pillars. And our source gives us 2 practical, production-ready examples of how these concepts come to life, using PySpark structured streaming and Delta Live tables for volume-aware streaming. Let's start with a PySpark structured streaming example. Imagine you're managing streaming IoT sensor data with dynamic volume handling, and you're using Delta Lake as the sink.
Right.
How it works is that you set up a Spark session to read from Kafka, which acts as that buffered ingestion layer we talked about earlier. You then parse the incoming JSON data, think device IDs, timestamps, temperatures, that sort of thing, and then write it to Delta Lake. The crucial part for buffering and microbatching here is a specific line of code. .trigger, processing time, 30 seconds. This directly controls that time-based microbatching.
That's the key control there.
Yeah, and you'd also use checkpoint location for exactly once guarantees, making sure you don't lose or double process data. Plus, the Delta format itself is super efficient for streaming rights and later analytics.
Very efficient.
Now, if we look at the Delta Live tables, or DLT example, this is about building a volume-aware streaming pipeline with maybe a higher degree of automated management.
Yeah, it's more managed.
The highlights here are really compelling. DLT uses Python decorators like at dlt.table to automatically handle dependencies, data lineage, and refresh policies. It does a lot for you. It has built-in support for both microbatch and continuous processing, automatically scales resources. Databricks manages that for you, and includes built-in checkpoints and retries. It sounds easier.
It can be simpler to manage, definitely. So when it comes to choosing between PySpark and DLT, you're really looking at a few key trade-offs.
Right.
For example, if you crave granular control over your microbatching timing and logic, PySpark is your go-to. It offers high
A
precision.
wooden box to turn.
Exactly. Whereas DLT takes a more managed approach, giving you medium control, let's say. But then, if ease of orchestration is paramount, DLT shines with its fully managed auto-lineage features. PySpark would require more manual setup, more boilerplate, perhaps.
Ah.
When we talk about scaling, PySpark allows for Spark's own auto-scaling configurations, which are powerful, but DLT has it built in with serverless options that are incredibly flexible and often simpler to configure. For governance, PySpark needs manual tracking. You build that yourself. DLT offers built-in data quality rules and lineage tracking.
That's a big plus for DLT.
It can be. And finally, for simplicity, like you said, PySpark generally requires more coding, while DLT is declarative and often easier to maintain in the long run.
That comparison really helps paint a picture of when one might choose one over the other.
Yeah.
Very useful. Now let's dive into a concept that is critical for any real-time system, but can sometimes feel a bit abstract. Watermarking. It's how streaming systems manage the inevitable challenge of data arriving out of order or, well, just plain late.
Watermarking is absolutely critical in streaming, because it helps you balance between data completeness, getting all the data, and system latency, getting answers quickly. It allows for the processing of late-arriving data, but only within a controlled window. And importantly, it automatically drops data that is simply too late to be useful anymore.
Okay, so how does that work? What are the terms we need?
Right, let's break down a few key terms. Event time is the actual timestamp when the event happened out in the real world. Processing time is the timestamp when your system processes the event. These can be different.
Definitely.
The watermark itself is a dynamic threshold. Think of it as the system saying, I've processed everything up to this event time, maybe plus a little buffer. It determines how late an event can arrive and still be included. Windowing refers to dividing event time data into fixed time buckets, like 5-minute windows, for aggregation. You group events that happen around the same time. Late events are simply those events that arrive after the system's watermark has already passed their event time, but they're still within the allowed lateness window. And finally, dropped events are those very late events that exceed even that lateness threshold defined by the watermark. They're just ignored too late.
So to make that concrete, imagine your watermark is currently set at 10:00:00:00 a.m. on June 18th, 2025. And you decide, okay, I can tolerate events up to 5 minutes late.
Right, a 5-minute lateness window.
An event that comes in with a timestamp of 09:58.000 a.m. would be accepted, even if it arrived a little late, as long as the watermark hasn't passed 10:00:00:00 a.m. yet.
Makes sense, it's within the window.
But an event from 09:54.00 a.m. that's more than 5 minutes late would be dropped if the watermark has already advanced beyond 10:00:00.
Exactly, it missed the boat.
And in PySpark, you'd see configuration keywords like with watermark event time 5 minutes to set that tolerance right.
Precisely that.
And group holds event time 5 minutes in a dead device side to define those time-based groupings. This all works in tandem with microbatch triggers and checkpointing to ensure robust processing, and you can even monitor watermark progress right there in the Spark UI, I believe.
You can, yeah. It gives you visibility into how far behind processing might be. It's a precise dance between timeliness and completeness. So in essence, buffering and volume-aware streaming. They're not just technical optimizations, they are really fundamental to building resilient, intelligent, and scalable real-time data pipelines. They ensure systems can gracefully handle variable data loads without compromising performance or, crucially, data integrity.
And that's really the value proposition here, isn't it? By moving beyond just, blind ingestion and embracing techniques like microbatching, backpressure, dynamic resource scaling, organizations are unlocking the full potential of real-time analytics. It's how enterprises achieve reliable, low-latency processing with optimized compute efficiency, even when faced with the most unpredictable data flows. It's how things don't break.
Yeah. Exactly. It's about building robustness in from the start.
So thinking ahead. As data continues to grow exponentially, just relentlessly pushing the boundaries of what our systems can handle, how do you see these intelligent buffering and volume-aware strategies evolving next? Will they become even more predictive, perhaps anticipating surges before they even happen? Or will, maybe, new paradigms emerge entirely to handle the next wave of information?